Here is our agenda for today. We start with the system configuration of pyrolysis GCMS, then fundamentals of pyrolysis. After that, we will talk about the multi-mode pyrolyzer, its operational modes and the method map, as well as the sample preparation and what sets our technology apart from others. And then at the end, we have some application notes presented by Dr. Terry Ramis. Pyrolysis GCMS is a powerful and straightforward technique that utilizes a Frontier pyrolyzer as a programmable temperature inlet to a gas chromatography-mass spectrometer (GCMS) system. Here, as you can see, is the system configuration for pyrolysis GCMS. The pyrolyzer, shown as number 2, is directly connected to the GC injection port. There is no transfer line, there is no active site, and also no cross-contamination. You can also see some of the accessories, such as the microjet cryo trap that is shown as number 4 and uses the liquid nitrogen to trap and focus lights and volatiles at the head of the GC column. Number 3 is the selective sampler that is used for the hard cutting mode of operation, and I will discuss this shortly. And you can also see the auto shot sampler shown as number 1 that automates the analysis for 48 samples, and also number 6 that is the vent-free GCMS adapter and allows the switching of the columns without venting your MS. So now let's talk about how the multi-mode pyrolyzer can expand the capabilities of your GCMS system. As you can see, substances at ambient temperature are gas, liquid, or solids, mostly depending on their molecular weights. Materials that are soluble in solvents can be analyzed by GC or LC. Of these materials, about 30% can be analyzed by GC and roughly about 85% by LC, but with the proper solvents. However, as you can see, there are some insoluble materials that cannot be analyzed using LC, LCMS, GC, or GCMS. But these insoluble materials can be analyzed by pyrolysis GC or pyrolysis GCMS. In fact, when you're using pyrolysis GCMS, a solid sample can be analyzed as is, and there is no need for any solvent extraction or sample preparation prior to the analysis. So the entire range of organic materials, from gases to solids, can be analyzed by pyrolysis GCMS. And that's one of the advantages of the multi-mode pyrolyzer and how it can really expand the capability of your GCMS system. All right, now let's talk about pyrolysis. So what is pyrolysis? By definition, pyrolysis is a thermochemical decomposition of organic compounds at elevated temperatures without the participation of oxygen. Most often, this technique uses an inert gas, such as helium, and then using this technique, a sufficient amount of heat breaks down the organic bonds of a complex mixture into smaller and more stable molecules called the pyrolysates. The pyrolysates form and their relative intensities then provide insight into the nature of the original composition. It is very important to mention that applying the sufficient amount of heat and identifying the appropriate temperature for programming the pyrolyzer's furnace are critical factors in pyrolysis technique. And as we go more into details, you'll find out how to identify that sufficient amount of heat so you're not over or underheating your samples. So as we just discussed, in pyrolysis, a sufficient amount of heat breaks down the organic bonds of a complex mixture into smaller and more stable molecules. So there are 3 main degradation mechanisms for polymers: random scission, depolymerization, and side group elimination. For random scission, polyolefins such as polyethylene, polypropylene, and polybutylene are good examples. In this case, the CC bonds break to produce fragment patterns of increasing oligomer sizes. So you'll see all these alkene and alkanes fragmentation. In a depolymerization category, the polymer thermally degrades into its monomeric fragmentation. Polymers such as polystyrene is a good example, which in this case breaks down to its monomer. Styrene monomer shows as S, dimer, double S, and then the trimer. In a side group elimination, polyvinyl chloride PVC is a good example, where the side group, in this case the Cl that is attached to the side of the polymer chain, breaks before C bonds. So Cl removes the hydrogen from the polymer chain, which causes the unsaturated polyenes plus HCl. Then these unsaturated polyenes start forming aromatic rings. So as a result, as the fragmentation of a PVC, you'll see HCl and these aromatic rings. Polymeric materials often contain a variety of additives. These compounds are identified using some of the commercial mass spectral MS libraries, but these general purpose MS libraries contain very few entries for pyrolysis and additives, which extremely limits their utility for polymer characterization. So Frontier Laboratories developed a search engine and libraries that is called FSearch. The ions associated with hundreds of polymers, their degradation products, which are also the pyrolysates, and hundreds of additives are used to identify and thus characterize the sample as it is heated in the pyrolyzer. So FSearch is a search engine with 4 unique libraries for identifying additives, volatiles, light compounds, as well as oligomers, heavy and polymeric compounds. FSearch also allows you to create your own user library. We also call it in-house library to perform contamination, comparison, and failure analysis. FSearch has other features like the ability to overlay different chromatograms. You can extract different M over Z ions, and also an integrated sum analysis where the FSearch engine can integrate the whole pyrogram, then make an average mass spectrum, and then identify the corresponding polymer. This book, as you can see here, is used along with FSearch and the MS libraries as a reference. The book has pyrograms, EGA thermograms, and also MS data of major pyrolysates for many polymers. It also has detailed information about the peak assignment tables and EGA thermograms of each polymer. Here I'm showing an example page from the book for pyrolysis GCMS of polyethylene. And as we discussed, polyethylene goes through the random scission. As you can see, the pyrogram of the polymer, in this case the polyethylene, that was performed at 600 C is shown as number 1 category. Then number 2 is the peak assignment table together with the molecular weight, relative peak intensity, and the retention index. And then number 3 is the EGA thermogram that was performed from 100 to 700 C at a rate of 20 degrees per minute, as well as the average mass spectrum of the EGA thermogram. And number 4 category is the mass spectrum of the top 10 major peaks. So FSearch is a search engine software that contains all that information from the book. So now that we know what is pyrolysis GCMS system configuration, let's talk about the multi-mode pyrolyzer and how it works. As the name says, using the multi-mode pyrolyzer, multiple analyses can be performed on a single sample. So this is really another advantage of the multi-mode pyrolyzer, where its furnace can be used for multiple analytical techniques, in addition to flash pyrolysis. In fact, the multi-mode pyrolyzer can be used for evolved gas analysis, EGA, thermal desorption, even multi-step thermal desorption, hard cutting, and reactive pyrolysis, in addition to true flash pyrolysis. We have created a series of techniques referred to as the method map to chemically characterize samples using the multi-mode pyrolyzer. Now that you have all these modes of operation, which one would you start first? When you're analyzing your sample, which mode of operation will you be using first? So the method map provides step-by-step guidelines for material characterization. EGA, Evolved Gas Analysis, is your first step, which provides a clear picture about the thermal profile of a sample, as well as the optimal temperature zone for the next step. So really, EGA guides you what to do next. It will show if a thermal desorption, hard cutting, or flash pyrolysis is needed, or even if a combination of the technique is required. To perform EGA, a short and deactivated tube is used to connect the GC injection port to the MS. The sample is dropped into the multi-mode pyrolyzer furnace, which is at a relatively low temperature. Actually, it could be as low as 40 C. In this example, we are starting the temperature at 100 C, as you could see in this figure. The furnace is then programmed to a much higher temperature, for example, 600 to 800. In this example, is going to 700 C. So we're programming the furnace from 100 C to 700, 20 degrees per minute. Compounds evolve continuously from the sample as the temperature increases. So then a plot of detector response versus furnace temperature is obtained, as you could see in this figure on the right-hand side. Your x-axis is the furnace and the temperature, furnace and your sample temperature, as well as the retention time, and then the y-axis is the intensity. So now by looking at this EGA, you have a clear idea about the thermal profile of your sample. Do I have any additives? What are my additives, or how heavy or how light the polymers could be? After obtaining your EGA thermogram, then you can analyze the peaks using the FSearch EGA MS library. If it's needed to further analyze the sample, EGA guides you to the next step. So you might want to perform a thermal desorption, which is used for analyzing additives and volatiles. However, the key point here is that you thermally extract the additives and volatiles from the mixture. So any sample preparation or solvent extraction step is eliminated. Or you could perform flash pyrolysis, which is also called single shot, and it's a fundamental technique for your polymer analysis. So in this mode of operation, the furnace is typically programmed at high temperature to break down the polymeric and heavier materials into smaller fragmentation. The key here is that you are performing a continuous and a true flash pyrolysis, where all the pyrolysates are directly transferred in a single step into GC as they are generated. Heavy and polar compounds are also directly placed on column, and light compounds are not lost. As you can see from the figure in the middle, you could also do a double shot GCMS analysis that is performing two analyses on one sample, thermal desorption followed by flash pyrolysis. So first, the additives, the volatiles, and lighter compounds are thermally extracted from the mixture, and you obtain a thermal desorption chromatogram. And then the flash pyrolysis is performed to analyze the heavier polymeric compounds from the pyrogram. You can also do hard cutting, as is shown on the right-hand side. In this case, the EGA thermogram is thermally sliced into multiple temperature zones, depending on the thermal profile obtained from the EGA. And we will have an application note on hard cutting very soon. So now let's take a closer look into the double shot mode of operation using the multi-mode pyrolyzer. This is the double shot analysis, which is the thermal extraction of additives and volatiles from the polymer. First, your EGA is performed using the EGA tube. In this case, 100 to 700 C, 20 degrees per minute was the EGA programming for the furnace. and as shown here, the EGA thermogram is then obtained. To further analyze the peaks from the EGA tube is then switched to a separation column using the vent-free GCMS adapter. Then the furnace is programmed from 100 to 300 C, 20 degrees per minute, to obtain the thermal desorption GCMS chromatogram that corresponds to any residual solvents, monomers, additives, volatiles, and lighter compounds. And then the second shot is the flash pyrolysis, where the furnace is programmed at 600 C based on your EGA thermogram to analyze the heavier and polymeric compounds from the obtained pyrogram. So this is called double shot analysis because two analyses are being performed on one single sample, thermal desorption followed by flash pyrolysis. If there are more than two zones in your EGA thermogram, hard cutting technique, which utilizes an accessory called selective sampler, it slices the thermal zones out of the sample and separate the components chromatography with detection by the MS. So sample preparation is very straightforward and efficient in pyrolysis GCMS, depending on your sample type. If it's a liquid or solid, you can use the appropriate sampling tools and place your sample into a sample cup. We call these are inert sample cup, and we call them eco cup. So solid samples can be analyzed as is. There is no need for any solvent or sample preparation before the analysis. You simply place your sample into a cup and then place your cup into an auto shot sampler, and it automates the process, or you could manually inject it into the furnace. My last topic before turning to Terry for application notes is talk a little bit about the different technologies, pyrolysis technologies in the market. So as you could see here, there are three different technologies in the market for pyrolysis technique: filament, curry point, and also the vertical microfurnace. I'm going to start with the microfurnace technology. So microfurnace technology allows a full range EGA, evolved gas analysis, to obtain a thermal profile of an unknown sample for light compounds, volatiles, and additives, as well as oligomers, polar, and heavy compounds. The EGA experiments can be performed from 40 C to more than 1000 C and correlate results to the well-established TGA, thermal gravimetric analysis techniques, throughout the entire temperature range of the experiment. And as you know, this capability is critical for evaluation of unknown samples. Microfurnace technology directly deposits all the pyrolysates on column in a single step for a continuous mode analysis. The sample is placed in an inert cup held at ambient temperature in helium and is not subjected to heat prior to the analysis. The microfurnace has been heating to the desired temperature, which is precisely measured with a thermocouple sensor located next to the sample that it will be pyrolyzed. The sample cup then drops into the quartz pyrolysis tube, where the sample is rapidly and reproducibly pyrolyzed. The pyrolysates are directly swept onto the GC analytical column for separation and detection by the MS or any other detector that you choose. This single-step process of the microfurnace allows low and high molecular weights as well as polar compounds to be detected and analyzed. The absence of any switching valves and transfer lines is critical for the ability to detect heavy and polar pyrolysates as well as additives. The microfurnace technology also guarantees reproducibility and accuracy of the temperature within plus or minus 0.1 degrees Celsius. All surfaces are quartz or temperature stable deactivated. There is no transfer line with any cold spots and no cross-contamination. Frontier Pyrolyzer is based on a vertical microfurnace technology that performs a one-step pyrolysis. With Frontier technology, all the pyrolysates are directly transferred on column in a single step. There is no switching valve, no trap, or no transfer line. So a full range analysis for detecting low and high molecular weights as well as polar compounds can be performed. As you could see here with the microfurnace design, using FID as the detector, C100 can be detected. This is because with this technology, the polar and heavy hydrocarbons are directly and continuously transferred on GC column as they are generated. On the other hand, filament pyrolyzers can suffer from poor temperature accuracy and poor reproducibility because of the non-uniform heating. Sample placement and heat transfer variations affect the temperature of the sample, depending on where the sample sits in relation to platinum wire coils and the sample contact. The filament temperature is estimated from the electrical properties of the wire, but the temperature of the sample is not actually measured as it changes over time. The sample must be inserted prior to the pyrolysis into a heated manifold to avoid condensation of the pyrolysates. And this preheating step causes degradation or thermosetting of samples and evaporation of volatiles and semi-volatile compounds in the sample prior to your analysis. Some filament pyrolyzers use a two-step process in which some of the pyrolysates are first collected on a trap. Then a switching valve sends the pyrolysates from the trap through the long transfer line into the GCMS. During this two-step process, polar and heavy compounds may be stuck irreversibly in the trap or are not transferred for analysis because of the cold spots in the system. The curry point pyrolyzer can have a high heating temperature accuracy. However, the heating temperature depends on the alloy composition of the sample foil. It is therefore impossible to continuously raise the heating temperature of the curry point device to allow for the EGA techniques. The preheating of the heater manifold is also needed, similar to the filament pyrolyzer, so the results vary depending on how the sample is wrapped with the alloy foil, and this leads to a very poor reproducibility. Also, as the sample is exposed to heat prior to the analysis in a heating manifold, degradation and thermosetting of the sample happens before starting the analysis, which results in evaporation of volatiles and semi-volatile compounds prior to your analysis. So what sets microfurnace technology apart from others? With a direct connection to the GC injection port, no transfer line, no switching valve, all pyrolysates are directly transferred in a single step into GC as they are generated. Heavy and polar compounds are directly placed on column, and light compounds are not lost. The sample placed in an inert sample cup is held in an ambient temperature and is not exposed to any heat prior to the analysis. Therefore, there is no chance of evaporation, degradation, or thermosetting before the analysis. Also, the sample is purged of oxygen before heated so that there is no oxidation reaction. Critical for evaluation of unknown samples, the Frontier microfurnace technology can perform full-range EGA, evolved gas analysis experiments from 40C to 1050C, and correlate results to the well-established TGA, turbo gravimetric analysis technique, throughout the entire temperature range of the experiment. The microfurnace pyrolyzer also controls the actual sample pyrolysis temperature to within a plus or minus 0.1 degrees Celsius. But other pyrolysis devices only control the temperature of the heating element and not the actual sample temperature. So that's all I had for today. Thank you for your attention, and I would like to pass it to Dr. Terry Ramis for some of the application notes.
Thank you, Rogine and Lauren. And now I'd like to take the group through some application areas. And what I have here is shown a list of typical applications. We have them categorized, as you can see, by what we call the material type. And one of the things to notice is all of these materials are things that would, of course, normally not be amenable to full analysis by gas phase GCMS techniques. Some of these are, polymers, plastics, fibers, different structures of the organic polymer, that's one way to look at it. Other applications are additives that would be contained within the polymer and performing an analysis on those in the matrix. And then, of course, there are particular products such as inks and paper. Paper has coatings, inks has chromophores, dyes and pigments attached to polymeric materials with different particle sizes. Of course, in other product areas, personal care products, medical device, and food packaging are examples. And then it gets into a little bit different area, biomass and energy. So energy would be looking at high molecular weight rock or shale material that would have hydrocarbon content in it would be an example. And then biomass, biomass basically is plant-based material. And in this arena, it's typically the frontier application is to look at biomass, analyze what's contained in it, what's the cellulose, what is the lignin, what is other content in there, and how would that be amenable to use in energy or in other specialty chemicals. I already mentioned shale oil above, along with the energy. And then forensic work that can often be involved with fibers or coatings and other kinds of environmental samples. So that gives us a range of applications. So in going through different applications, the first thing I want to start out with is the use of the evolved gas analysis, or the so-called EGA technique that Rogine has shared with you. And this is a very quick analysis. We treat the sample thermally, just as we would in a thermal gravimetric or a TGA experiment. And so we're going to, she's indicated, ramp the temperature at a, let's say, 20 degree per minute heating rate from maybe 100 degrees up to 800 degrees C. So over here on the right-hand side, we have 4 EGAs. And in this case, the top one is a so-called unknown sample. So this would be the candidate that someone is looking at in a QC environment or in a competitive environment, failure analysis application. And the question is, what is the matching candidate? So if you just look at the thermal profile of the first candidate versus the unknown, it turns out that the thermal profile matches. And then when we go over and we look at the mass spectral information, we see that that also matches. Now, if we went to candidate 2, you can see that the mass spectral information by itself is also pretty close and would be difficult to distinguish. However, because we ran the EGA analysis, we see that there is a thermal component that comes out prior to the matching thermal component in the unknown sample. So because of the EGA, we quickly know that we have a blend. And then, of course, candidate 3 has a similar thermal profile, but the MS data would quickly tell us that it is a different chemical composition. So, of course, in this case, the unknown sample most closely matches candidate 1, which in this case is a PET material. So just a really nice example of how quick EGA can be used to do a quick characterization of the sample. Now, other things that we can do, in this case, what we're going to do is we're going to focus on the gases that are coming out of the sample. And in this case, it's going to be during a curing process. There are many examples of where we're going to be interested in looking at gases coming out of a polymer, for example. So in this case, we're going to have two components that are present. One is the bis phthalate anhydride, and the other is the dianiline sulfate material. And those are going to be present in the sample, and in a process environment, they're heated in two steps. So there's a first step heating process, and some reactions happen, and there's a second, it's followed by a second heating process to fully cure. And so down below, we have an EGA run here, and what we're able to do is to see where these two different steps happen. So as we heat the sample from 120 up to 450, and we can change, of course, the rate to do that. We see water coming off here in green, and then we also see the dimethyl acid come off, but it comes off just in the first heating step. And then, of course, we see carbon dioxide coming off, mass 44. And then as we enter the temperature that would correspond to the second heating step, we begin to see the SO2 come off, and we begin to see the aniline come off. And now we no longer see the dimethyl acid amide. So this is just an example. I said it's one of many in which we can look at off-gassing. Other tools that we have are we can add UV light, or we can add air to do oxidative and light-based degradation studies and see off-gassing as well. The kind of sample here, one of the big differences is that now we're going to have a combination of an inorganic material with an organic, possibly a binder, for example. So a ceramic composite material. Of course, the inorganic material in this case will stay in the cup, and yet we're going to be able to look at the organic content. So if we do an evolved gas analysis from 100 degrees up to 500 in this case, we then with the mass spec evaluate the regions we have, and we see that we have 4 different regions along the evolved gas analysis that contain different kinds of chemistry. So in the first zone A, we see a 149. Later, with a technique called heart cutting, we would determine that this was a phthalate or a combination of phthalates. And then in zone B, as we thermally look at the sample, say from 200 up to above 300 degrees, we see saturated hydrocarbons coming off. And again, we could do a detailed analysis of this particular fraction or zone with a heart cut technique. And then in zone C, you can see that we're now starting to get into a temperature region that might begin to introduce some pyrolysis, and we start to see some polymers. And when we do a library search with the library that Rogine showed you, we get a match for PBMA or polybutyl methacrylate. And then it is a blend, and so we have then zone D, where we are able to see, again, by using the library and matching with polystyrene. So here we're able to see components throughout the thermal range, and we're able to also see them in inorganic mixed matrix. This particular analysis, thermal desorption, is going to be the basis for some of the applications I'm going to show later, in which, of course, it's more complicated. This is pretty straightforward. BHT is a common antioxidant. You can see the structure down here, present in polymers. Nowadays, the functionality is generally on a much bigger molecule so that it stays in the polymer and doesn't come out with time. But in this case, by simply doing our EGA, we're able to see that the polymer doesn't come out until over 400 degrees, but yet the additive comes out quite early. What we can then do is we can just heat the sample up to, in this case, 200 degrees C, trap it on our fully integrated and automated cryotrap, and then we can do a chromatographic separation. And of course, in this case, we can easily look at the BHT, and we can, of course, confirm that with mass spectrometry. This is being done at 500 part per million, and of course we can go down, certainly into the very low part per million quite commonly with that. And you can see that the reproducibility also is very nice in about the 3% RSD range. In this case, our thermal desorption gets more complicated. So obviously the last one was a very easy example just to introduce thermal desorption and to introduce how we find the temperatures to use. So in this case, we're going to be looking at more challenging additives. You can see them over here on the left. These are common additives for a variety of purposes that are present in a wide range of polymers, and they're much larger. They have some polar functionalities, and so they're more challenging. And the Frontier system, because of the inertness and the capability of quantitatively and reproducibly passing fairly large molecules into the GCMS, allows us to look at these. So again, we're going to heat the sample up, in this case up to 300 degrees C, and we're going to cryotrap again just the pre-pyrolysis zone, and you can see this is in a polystyrene sample. We have the conditions noted there as well. And now then, when we do a GCMS separation, we can now separate and look at each of these components. We can quantify them. We can use a standard addition technique to quantify them. In this case, what we're going to do is we're going to look at both the thermal desorption and the polymer backbone in what we call a double shot. So the system has the capability to introduce the same cup multiple times. In this case, two, one for the thermal desorption and looking at the additives, and in the second case, to pyrolyze the polymer from that same cup. So of course, in the lower GCMS run, which is done at 550, we're only seeing the polymer. And in this case, the reason we're only seeing the polymer is because the additives were removed during the first run of that same cup. So this we call the double shot technique, and we can do many of these. We can do actually up to 8 different sequential analysis of the same cup, and when we do more of them, we call it a heart cut. So this is, in this particular case, this was a rubber compound, an application of a double shot technique. So now let's look at how we might use this technology to reverse engineer, look at a competitive product, and do what we call a deformulation. And interestingly, what we're going to do is we're going to choose a cosmetic eyeliner. It might seem like a sample that you wouldn't think of initially, but it turns out that, as we'll show you, it has quite a range of temperature zones and polymer compositions and other additives. So it turns out to be an interesting technique, interesting sample to show the technique. We're going to do an EGA run, and then we're also going to do the heart cut. So we're going to sequentially look at the same sample multiple times, and we're going to do that within different temperature zones. These are the conditions that we use on the left for the EGA and on the right for the heart cut. So if we look at the EGA now, between actually 40 degrees and 500 C for this particular sample, only zone D and E actually contain the polymer material. You can see again, we're getting close to, we're getting into the mid 300 C and 400 C, where depending on the polymer, pyrolysis begins. Of course, by 700 C, all the organics would be gone from the sample. So actually going above 700 C is not necessary for looking at organic materials. So in this case, we can take the EGA and do extracted ion chromatograms, and that's what we have down here. We're able to see that we have maybe 1, 2, you can see here 3, 4, you can pick out 5 different zones by temperature if you look at it vertically. And that's what we do then to pick out the temperature zones that we're going to then use to look at more detailed later. And so what we then do is we cryotrap sequentially, take zone A, the first zone, cryotrap, do a GCMS, take the second cup and put it in the next temperature range, cryotrap, and do a GCMS, etc., until we get all 5 of those zones. And in this case, we have 5 different GCMS runs, but they come from specifically known temperature ranges within the sample. And so this helps with our interpretation, knowing that the early temperature components are going to be additives or small molecules that did not undergo covalent bond breakdown. And then, of course, the later zones are going to be pyrolysis, in which the backbone polymer was broken down into its small and known pyrolysates. And then, of course, we can go through and identify those. So there's 2 things that enable us to do this. One, of course, is the cryotrap, and we don't show that here. Most people are familiar with cryotrapping, but this is all, of course, run and automated by the software with the auto sampler. The other device that's used for this is a selective sampler. And the selective sampler sits on the bottom of the GC inlet. You can see the pyrolyzer is here, followed by the inlet. This is the GC liner with the split flow coming out as normal. And then this device attaches to the bottom, and it allows us to either allow the gases from the pyrolyzer to flow onto the GCMS column for cryotrapping and subsequent analysis, or it allows us to not allow any components to go onto the column, and we have a fresh helium supply that supplies the column here. So this is automated. It's a simple 2-position device, and it's what allows us to do this hard cutting in complex matrices. So the result here is that we see some moisture agents that are present in very small molecules at low temperature. We see a preservative that's present in the cosmetic eyeliner, and then a skincare agent present in the zone C. And then the actual polymer that holds the this particular component together is the polymethyl methacrylate. Followed by a PDMS siloxane to give it a shine or a smoothness to it. So this is an example of a deformulation to a product that would be common and a lot of people would be aware of. Now we'll change modes here. We'll look at an ASTM application. And so the focus of this is to look at the phthalate additives. Many of you may be aware that there are some regulatory requirements that have emerged over the last number of years. And so characterizing the levels of phthalates in polymers and other complex materials is an important thing to do. And this can be done rapidly by thermal desorption, GCMS, with the Frontier system. It can be done with a single quadrupole or with more complicated tandem quad or triple quad techniques. And you can get a application afterwards by requesting that. So thermal desorption is really just defined as heating the sample up to allow vaporization of a component from the matrix prior to pyrolysis of the matrix itself. So in this case, if we have a polyvinyl chloride or a PVC, we're going to leave the PVC in the cup, and we're going to then remove the additives, in this case, the phthalates. And we're going to, for small phthalates, we would of course use cryotrapping. For the regulatory phthalates, we do not need to use that because they're heavy enough that they phase focus on the front of the column. And so this technique is done with no solvent extraction. These are some common other additives that you might use the same technique for. So I'm just talking now about phthalates and polymers, but you can look at brominated compounds. I already showed you an application, the first one there with additives and polymers, bisphenol A and antidegradants in rubber. So it can be done, this can be done in 2 different ways. Now, if the polymer can be dissolved in a solvent, then we can, but we don't have to, we can take the sample and homogenize or take a small piece of the sample. We can either explore heterogeneity or homogenize a sample. And then we can take that powder that results, weigh it out, and dissolve it in a solvent. And then we can take an amount of that solvent, put it in the sample cup. We can, if we need to, evaporate just the solvent gently, and we can analyze it direct by GCMS. So that's one technique in which we're going to dissolve the solid. Now, some polymers, of course, many polymers cannot be dissolved in a solvent. So in that case, we would use the direct method. In that case, we take the powder itself, place it in the cup, and look at it by GCMS. And this is ASTM 7823 for people who want to look at that later. Now, if we were to begin, of course, with the evolved gas analysis, we would see as we go from low to high temperature that we have the phthalates and other additives come out. We actually have an HCl elimination, which is part of the mode of degradation of polyvinyl chloride, and then the main pyrolysis of the remaining PVC backbone, shown here between 400 and 500 degrees C. So if we stay in the, say, mid to low 300 C range and below, then we're going to leave the matrix in the cup and we're just going to look at the additives. So that's what we do in this technique. This is just showing the extracted ion chromatograms, and for example, you can see the HCl. We're going to go ahead and have the HCl go onto the GC column in this case, but it's of course very easy to separate. It does not interfere in this particular technique. DINCH is a non-phthalate additive that's commonly in place along with phthalates, and so we're going to distinguish between the DINCH and the phthalates by both GC resolution and by MS, mass to charge specificity, using thermal desorption sample introduction. So this is an example of the total ion chromatogram on the top, and then of course the extracted ion chromatograms for each component of interest, along with the mass to charge for that particular component. And you can see that some of the phthalates are a single compound, while other phthalates are actually a distribution, as the ester chain can have a range of isomers. So that's the case here of the DINP and the DIDP. We have to, be cognizant as to the use of looking at compounds that have the same mass to charge ratio. In this case, we have the example of DCHP and DEHP, in which the mass to charge ratios that we would like to use are the same. And in this case, it's okay because we're able to use our GC resolution. So we're using both, obviously, the GC separation as well as the MS selectivity. And of course, we could add a tandem or a triple quad if we wanted to have additional selectivity. And then we show here on the red curve, we have solvent extraction with external standard showing the precision. And then we have the thermal desorption with standard addition shown here using the Frontier technique with GCMS. And you can see the kind of percent RSDs that we get on that analysis here, in this case for 6 of the phthalates. And then these are using the extracted ion information for the particular component. DNOP and DOTP closely allude. So again, that's an example where we have to just be aware of interferences. And in this case, we're able to separate those by using different mass to charge ratios. So there's a previous case I showed you where GC provided the separation, and in this case, a very close case in which the MS selectivity provides the separation. And then we might have phthalates in things other than PVC. And so using the book that Rogine has already showed you, where we already know the temperatures and the detailed pyrolysates of all the common polymers, copolymers, and therefore blends, we can determine the thermal zone that we would use to look at phthalates and some of these other polymers. Polycarbonate, polystyrene, and polyethylene happen to be the ones that are shown here. And of course, that's the EGA that's allowing us to confirm those temperatures that would be appropriate for a different plastic or polymer. And then, of course, this can be used to quantify phthalates in products. This here is a power cord, and sometimes the concentrations can be quite high. So sometimes people will use a pre-screening technique and then eliminate the high concentration phthalates and then go back and look at the lower concentrations. The ASTM method, works in the 0.1% range, and of course, as I've shown you, this can go down to much lower concentration levels.